Good morning, everyone. Good morning, everyone. My name is Akhil. I manage the Dropbox infrastructure, and I wanted to thank you for coming to this session. I'm extremely excited to be in front of you to talk about how Dropbox leverages AWS and SQS to run massive workloads. And at the end of this talk, I would like to make sure that you not only get a sense of the operations and how we solve this particular problem, but also get a few takeaways which you can take back and see if they apply to the problems you might be trying to solve in your companies and in your infrastructure. Hopefully, most of you are aware of what Dropbox does. We are the world's largest cloud storage and syncing company in the world, with over 300 million users syncing more than 1 billion files every day. Just to give you a sense of how big we are, we believe we are the largest repository of Office documents in the world with more than 35 billion documents in Dropbox right now. That's 5 documents for every living human being on the planet right now. So that's a huge amount of scale. This adds up to hundreds and hundreds of petabytes of data which we have to store and synchronize across hundreds of millions of devices every single day. And the way we achieve this scale is by leveraging a hybrid architecture where we use the power of Amazon and various services that it offers, things like EC2, S3, ELB, Route 53, SQS, as well as our own servers in the data centers which we own and operate. Our data centers are spread across the US between East Coast and West Coast, and are primarily used to store metadata about the users, the files they have, the revisions, and other business logic which we use to synchronize the data. Whereas we leverage Amazon to provide us with this almost infinite and flexible resource where we can keep growing without or very little operation support and actually use things like S3 to store our file content. In order to understand this better and see how this actually allows us to do synchronization across millions of users and hundreds of petabytes of data, let's walk through an extremely simplified version of how syncing works. Imagine you have a client. It could be an iPad, a phone, or a desktop client. And there's a document in your Dropbox that the client has to upload to the cloud. The first thing that it does is it takes the document and separates it out into 2 parts. The first part is chunks of 4 megabyte blocks, which is the actual content, the bytes in your file. And the second part is what we call the metadata about the file name, the path on your computer where the file is located, the revision number, the actual list of blocks keyed by the hash of the block which constitute that file, and several other attributes which we use to provide a richer experience and use it to make sure the syncing is done correctly. Once this is done, the client takes the metadata of the file and sends it to our servers in our data centers, asking to say, hey, can you commit a new revision of a file? So if it's a new file, this will be revision 1. On getting this request, the first thing that the servers do is check whether we have the blocks before we commit a new version. Obviously, if we commit a new version and we don't have the block, that's a bad thing. So if it's a new file, as in this case, we'll end up saying, no, we don't have the blocks. We have never seen this file before. And tell the client that you need to upload the blocks before we can commit a new file. On receiving this message, the client knows that now it has to upload the blocks. So it takes these blocks, sends them to our servers running in AWS, and asks us to put them in S3. And this is where we actually store the content of your files in S3 in 4 megabyte blocks. Once that is done, the servers then notify both the client, hey, the blocks are successfully uploaded, but also our servers in Dropbox data centers to make sure that we record the fact that we have these 3 or 4 new blocks in our repository. Once this is done, the client again then goes back to our servers and saying, look, you told me to upload the blocks. I did that. Can you now commit a new revision of a file? And again, our servers do the same thing. They check whether we have the blocks or not. But since we had already updated the information that we did upload these blocks, this time the servers will find that we do have the blocks and essentially tell our clients that the commit is done. And this is when essentially a file is synced. Obviously, this is an extremely simplified version of how syncing works. We have to, in reality, take a handle a lot of edge cases across different platforms. There are bugs or features, depending on what you want to call them, on each of these operating systems, which we have to take care of. We have to handle things like people going offline or shutting down their laptops while the syncing is happening, as well as multiple clients trying to update the same file. But hopefully, this gives you a very broad general sense of how our infrastructure is able to do what is the core functionality of our product, which is to synchronize data from your devices onto the cloud. What might be a surprise for a lot of you guys is that while syncing is an extremely important and one of the reasons Dropbox became so popular, it is actually a very, very small part of what we do. What we find is users who are using Dropbox heavily are not using it to synchronize and back up their data. They're actually using it to share their files with each other. There are people who come from wedding trips or vacations. They upload all their thousands of photographs, and then they share it with their friends. Parents are using Dropbox to share videos of their kid's birthday with the grandparents. People at work use Dropbox to collaborate on documents, to be able to work on an Excel sheet or an Office document. Remember, as I mentioned, we are probably one of the largest repository in the world for Office documents. And in a lot of ways, improve their productivity. And in all these use cases, it is simply not enough for us to be able to just synchronize the bits of a file across different devices and make sure you never lose them. We actually have to add value on top of the data. We have to make sure that when you're using Dropbox, you're not only getting the access to the data, but are also able to improve your productivity or make the workflows about sharing and collaboration better. And we call this essentially bringing your data to life. For example, we would like to be able to generate thumbnails when you upload photos from your fancy SLR camera, so that when you share your photos with someone who has an Android phone, they can view the photos immediately on their phone. We want to be able to generate previews for your Microsoft Office documents, so that when I'm working on a presentation like this, and I want to send it to my colleagues to get some comments, they can quickly look at the presentation on a web view as opposed to opening it on a native application. Another very good example of how we can leverage our infrastructure to bring data to life is something which recently launched for Dropbox for Business, which is a full-text search across all the documents. Remember, the scale we're talking about is, again, more than 35 billion Office documents. And allowing people to access their Dropbox and be able to search through the content of the document was one of the biggest and most frequently asked feature from our customers. And what people would end up doing is they would have a large Dropbox where they're literally working out of it, but they cannot synchronize all their content into their native desktop or PCs, and they would want to be able to search the content to know what files they were working on. And there are a lot more examples like this. Another example could be video transcoding. Videos is something which is extremely personal for people. They don't want to lose it, but they also want to be able to view the videos across multiple platforms, which means we have to transcode these videos in infrastructure. So a common theme, which hopefully you guys are getting a sense, is that a big part of our infrastructure is bringing data to life. And in order to do that, what we need to do is run extremely large workloads to process the files as they're being updated or uploaded to Dropbox. And if you may notice, these workloads essentially can generate either metadata. Examples could be EXIF data from photos, which allows us to sort your photos based on an attribute, or actually generate files like thumbnails of different sizes so that you can view them on your iPad, your Kindle Fire, on your phones, as well as on web. The challenge for us, though, is unlike a lot of these large, massive workloads which people want to run in a batch mode, these workloads require us to be extremely low latency. And the underlying need for this is the fact that people are now collaborating and sharing in almost real time. Imagine a person called Sam who is working late in the night, trying furiously to finish up a report that's due in a couple of days, and he feels that he has something which he would love Alice to take a look at. So he uses Dropbox. He sends a link from Dropbox to his colleague, Alice, and says, hey, check out the new updated doc. Now, in the old days, without the world, which is now hard to imagine, but when we did not have our smartphones or our tablets, it probably was reasonable to expect that Alice would probably get to checking her email in the morning. She would probably get to reading this document in like maybe 4 hours, maybe a day. But if she's anything like any one of us in this room, she probably has a phone which she's constantly checking her email. So what will happen is she will check her email, look at the link, and immediately want to see the preview of this document. And if Dropbox is not able to generate a preview of this document in this extremely short time span, the product looks extremely broken. People will not understand that this is a hard problem. People will not understand that it takes time. They will say Dropbox doesn't work. And that simply goes against what we believe in, that Dropbox should just make things happen magically. So that's the number one challenge. We have to run these massive workloads, but they need to be as fast as possible. At our scale, we have another unique challenge. We also have to make sure these things run at a very high throughput. To give you a sense of the scale we're talking about, what we typically see is tens of thousands of files need to be processed every second. And each of this file, by the way, generates more than one workload, because you can imagine a file has to be processed by multiple systems to generate thumbnails, to extract EXIF data. In case of a document, we need to process it to index it for search, as well as generate previews. As if that was not enough, we are in the business of storing users' content. And users' content can vary from small photos to extremely high-resolution photographs taken by SLR cameras, or documents which are 1 page to 50-page legal contracts. So there's a huge amount of variability in terms of workloads we have to do on the content. Moreover, the actual workload also changes a lot. So transcoding a video can take tens of seconds, whereas some other operations can take a few milliseconds. And if folks have designed systems, handling variability in your input is actually one of the most challenging tasks when it comes to performance. Last but not the least, all of us live in a world where innovation is the key to survival. And one of the things which we found, and we firmly believe, is that not only we have to build an infrastructure which allows us to do this, we also have to make it very easy for developers to add new kind of processing to the system. So they shouldn't have to go through this lengthy cycle of testing or making significant changes to the framework to add just another workload. So to recap, the challenge we are facing is we have to have a system which lets us run massive workloads with very low latency, with a high throughput, can handle variable workload, which can range from tens of seconds of processing to a few milliseconds, as well as flexible architecture, which allows developers to be able to dynamically change what gets processed and how it gets processed. If you had to take a step back and think about how we would solve this in an extremely naive way, going back to how I described the syncing, one can imagine that the first thing you might do is, the moment you commit a new revision, you know that you have a new file that you need to process. So why don't we actually go to Amazon, get the file, and start processing? It would work. And once the processing is done, we store the generated files back on S3 as well as metadata in our databases. This would work, but I'm pretty sure some of you are already noticing that this has a few issues. The first one is extremely high latencies. Remember that we talked about what we need to do is we want to make sure this entire processing happens as quickly as possible. In this particular implementation, we are shipping a lot of data, potentially tens of megabytes of data of a file. In case of videos, it can be easily a gigabyte of a video which people upload across data centers. It also has a huge cost to network bandwidth. And for something like us, where the scale is huge, we're talking about hundreds of gigabits of bandwidth. This is an expensive currency to pay just to do this processing. So obviously, we would like to avoid that. You might think that this is an easy problem to solve. So instead of shipping the data all the way from Amazon to our data centers to process it, why don't we do the opposite? Why don't we actually have our data centers send an RPC with some relevant information about the file and say, hey, a server in EC2, can you actually process this file, and I'll wait for the metadata. On receiving this request, the servers can process the file. They can actually do transcoding, thumbnail generation, extracting EXIF data from photos, generating previews. And once that's done, it stores the large files on S3, which is cheap because it's within Amazon, and then ships the metadata back to our data center to store it in our databases. Now, this solves the latency problem and the network problem to a large extent. We are no longer shipping potentially tens of megabits or even a gigabit of data between our data centers. The latency should be low. But this is where the fact that we store user content bites us. It still does not handle the problem of variable workload gracefully. Since our servers are making RPCs, which can result in workloads which can last up to tens of seconds, we see issues. We can easily see issues where RPCs either time out due to network issues, resulting in a higher failure, or we'll run into load balancing issues because some jobs will finish quickly, and it's very hard to be able to make sure all servers get equal amount of load. This system is also going to be extremely susceptible to backlogs because you essentially have a monolithic system which is saying for every file I'm going to start making an RPC. You can easily imagine that a particular kind of file can slow down the entire pipeline. So if tomorrow Apple decides to launch a new iPhone which has a fancy new video format, and one of the first things a lot of people do when they buy the new iPhone is download Dropbox, we might suddenly see a surge in videos being uploaded which take longer for us to transcode. That will not only impact videos in this case, it will also impact all other processing of all other documents. Your Word documents will not get processed, your photos will not get processed, which is not a good user experience. The last but not the least is it's actually very hard to change or add new data workloads because the moment you're doing this, it changes your network pattern. You have to modify both servers on our data centers as well as AWS. And any change you do to this system has to be canaried and tested very carefully, which goes against what our original goal was. We want to build a flexible architecture. So how did we solve this in Dropbox? In Dropbox, we took a first principle approach and I built this in-house system which we call Livefill, which is a highly scalable and configurable system which allows us to run various kinds of workloads, workloads which can span seconds to milliseconds in a graceful manner on files as they're updated in Dropbox in real time. This system has a lot of interesting properties. It uses SQS as a control panel to be able to manage how to coordinate and distribute the processing of files. It is not only highly scalable and reliable, it also handles the variable workloads extremely gracefully. And the best thing of all, it is very, very trivial to add new workload to the system, as I'll show you in a few slides. But before we get into the details of how Livefill works and how we were able to scale it up, I want to walk through a few concepts on which Livefill is based on. So one of the key insights which we had, which we used to build Livefill, was that all of these workloads or jobs which we run or we want to run on our files can be modeled as a series of handlers. Think of handlers as modules or classes which take an input, or a function which take an input of a certain kind. It could be a file of a certain type, or it could be binary blob in a format, say, protocol buffers, and outputs data of a certain kind as well, which again could be a file or it could be a binary blob. And these handlers can consume output from each other and use message queues to communicate with each other. Now, with this abstraction, suddenly you can start thinking of stitching together these series of handlers to create what effectively is a data pipeline, or something which can handle a particular workload. So you can imagine that you can define a data pipeline which says, I will take a photo and run these handlers in this order, and in the end generate the output we need to have. We also introduced a notion of virtual clusters. This was actually extremely important for us to make a performance system, which I'll talk in a little bit. But the idea here was that instead of having this huge, large, homogeneous set of servers which can run any kind of handler, we wanted to partition these servers into a smaller set of clusters which are configured to run only a specific set of handlers. And each of these clusters was associated with a SQS queue, which was one was an inbound, one was an outbound, and these clusters were completely isolated from each other. And with these components, Livefill system actually looks pretty simple. At a very high level, it's essentially a cluster, a series of virtual clusters. Remember, each cluster can run a specific set of handlers. Each of these virtual clusters have a queue attached to them, and this is how they communicate with the rest of the infrastructure at Dropbox. And they have access to our data in S3 so that they can read and write files back to it. In order to make it extremely flexible, this entire system is configured and managed by a single YAML file. This file defines the system configuration. It lets us know what kind of virtual clusters are we running, how many instances do we have in these clusters, what handlers are allowed to run on each of these clusters. And it also provides us with a configuration for each handler, which is essentially what kind of code do you want to run for this handler, which gives us a very easy way to modify or add or delete handlers. It also has specific details about what kind of input and output this handler is expected to consume and output. As an example, this is a snippet from the actual configuration which we use in Dropbox. And I've removed a few details to make it more readable, but you can see that the first 3 lines essentially talk about we have 2 virtual clusters. One is, as the name suggests, for Microsoft Office. The other one is for video transcoding. And then we have essentially a description of what is a data pipeline constitutes of. In this case, this data pipeline is for Microsoft Office. It has 2 handlers. One of them takes input in forms of files of Excel and outputs a binary blob. We use protocol buffers in our infrastructure, so this is essentially a protocol buffer. And then there's another handler which consumes the output of this handler and is able to output a file which is essentially an HTML version of your Excel files, which we can show when someone requests it on the web. And using this configuration file is extremely powerful because in order to add clusters or remove handlers or modify the handlers or even changing the code which these handlers run, you essentially have to modify this config file, which gets then automatically pushed to all our servers, and the system keeps running. So in this new architecture, let's go back and try to figure out how we can actually run massive workloads. So the first thing that changes is instead of making an RPC from our data centers to Livefill, we essentially send now a message, an SQS message, to the queues which are listening to which are tied to the clusters I just talked about. Once this message is received, each of these virtual clusters servers are constantly polling the queue to pick new messages, and the message gets picked by one of the servers. And based on the configuration which I just showed you, it knows that for a particular file type, what handlers do we need to run. So very likely, the first handler which gets executed for a particular file type will fetch the file from the file, execute the code which was defined in the configuration file, and then, again, using the configuration file we talked about, is essentially going to pipeline these data across series of handlers using message queue as an intermediary to be able to process the file and generate various outputs. In the end, what we expect is the system will generate either some files. Remember that what we discussed earlier, the workloads typically end up generating either files or metadata. So we can store the metadata back into S3 bucket, or if there is some metadata which we have to store, we push it out to the out queue, which then gets sent back to our servers in our data centers to be written to the databases. And while designing the system, we heavily leveraged Amazon and SQS. SQS was able to give us an extremely reliable delivery of messages. We not only could remove the complexity in terms of dealing with failures, dealing with RPC timeouts, or durability of a particular message getting lost in the distributed system, we also had no operational overhead of maintaining this system. So at a very basic level, you could imagine that we could use something like Redis or RabbitMQ instead of SQS. But in both these systems, we would have had to put in a lot of operational work to make things as reliable as SQS gave it for free. And as we will talk in a bit, it also scales to an extremely large number of requests. Even at our scale, we have managed to make sure SQS keeps growing as our user content and the usage of system grows. On the other side, since we are actually processing our files in EC2, it gives us the benefit to scale our workers very easily within seconds, depending on the workload. While we don't do this right now, you can easily imagine that we can stitch up the auto-scaling feature which Amazon provides to be able to shrink or grow these clusters as the load changes. And this is something which is extremely valuable when you are, again, dealing with user content where you have very little control on what gets into your system. Thanks to this and a bunch of other things which Amazon provided us, we're able to build and maintain this extremely large system with a team of just 2 engineers. Something I don't think would have been possible if we had tried to do this completely on our own. At the same time, while SQS and Amazon provided an extremely strong foundation for us to build this system on, there were a lot of things which we had to do to make it work and scale to our level of QPS and throughput. I wish I could tell you that we designed the system, we wrote up the code, and boom, it started working from day one. It didn't. It really does. There were a lot of mistakes we made. There were a lot of lessons we learned, both about how to use Amazon better as well as things we should think about when designing these kind of systems. And I want to share a couple of lessons we learned, and hopefully that will give you some kind of things which are useful even for the things you're working in your own companies. So one of the first earliest lesson we learned was use batch API. So when we started building the system and we're writing this code, we essentially said, oh, let's just send 1 message per RPC. And at the rate at which we were sending this QPS, it became very clear that that's not going to scale very well. Luckily for us, SQS exposes a batched API called send messages batch, which allows you to take, say, 10 messages at the same time and send them in 1 RPC call instead of 1 message at a time. And by doing that, we found that we could scale much, much better than what we were doing by just using a single API. The second interesting lesson we learned, this was somewhere in the middle of designing the system, and I call it simply as let's not try to be too clever and let SQS do all the heavy lifting. So one of the ideas we had, which was to improve the performance of our system, was that whenever a handler has free CPU cycles to process a message, instead of it then going to SQS, which is an RPC call, fetching the message and starting to process, can we actually aggressively prefetch these messages and store them in memory for the handler? And the idea being that this will allow a handler to essentially quickly, when it finishes up with a particular processing of a particular message, it can quickly look up in its memory and start processing the next message. Seems simple. It should theoretically cut down the round trip time you're making for every new message. But as it turned out, it was a pretty bad idea. And particularly for our use case where the workloads were extremely variable. What we noticed was what would happen is a server, since remember, there are like multiple servers doing this in a virtual cluster. One server would aggressively prefetch a lot of messages and store them in memory. But then all these messages would get backlogged behind a specific message or workload that, say, is taking tens of seconds. It could be transcoding a video, which is very long. And at the same time, we had other servers which were ideal, which could have actually handled these messages. But since the message was already claimed by the server, our throughput reduced. So we would see these unevenness in terms of some servers being extremely idle, some servers actually processing at their full capacity, but our overall throughput would not scale as much as we would like. So we changed it back where we said prefetching of these messages does not work, and wanted to and let handlers fetch the message as they're able to process them. The third lesson which we still follow is almost an axiom, which is we have to make sure that the pending messages queue on SQS is almost always near 0. This is essentially the biggest signal you will have in terms of whether your capacity to process incoming load is higher than what you are seeing from your clients. You can consider using auto-scaling, as I mentioned before, to scale up your workers if the load increases. But watching this and making sure that we react to this is an extremely important part of this design. If things start backing up, bad things will happen. However, no matter how well you do capacity planning, you can use auto-scaling, you can build it and have good quality control in a system. All of us know bad things can happen. In this case, it could be because of an increased workload. As I mentioned, we don't control the content users are uploading to Dropbox. Something might change on their devices. Something might happen where Google or Apple launches a new phone, and suddenly we see a far higher resolution photos than what we were seeing earlier. There could be bugs. We have actually shot ourselves in the foot a lot of more times than what I would like to admit here, where we have introduced delays in our processing and made things slower, or network issues. Things like fetching files from S3 could become very slow, which can cause issues in the system. But all of these causes often result in a common symptom, which is backlog. What you end up starting seeing is that the messages which are being built up, the number of pending messages in SQS is growing, and it doesn't seem to be decreasing with time. And in this state, it is actually very, very easy to enter a state where system will not recover unless you start aggressively shutting down the input traffic coming to the system, which is an extremely bad experience for our users. So the key here is, while making sure that in steady state things work, but also building enough logic and smartness in your system that graceful degradation and automatic recovery is a first-class citizen. And that's what we spent a lot of time actually building in our system to make sure whenever any of the issues like bugs or network issues happen, it does degrade the service, but it does it in an extremely graceful manner, minimizing the impact to the least number of users as opposed to the entire system falling over. So the first step there, which was, again, a very good learning experience for us, was building deep insight into our system. In an extremely complicated data pipelining system, it is extremely hard to know what is causing a backlog. As I explained, the causes could be anything. It could be network issues, it could be bug, it could be new code, it could be new content, but all you see is a backlog. So being able to dig deep into the system and see where the issues are happening required us to invest in building extremely powerful profilers of this entire pipeline. We instrumented the code and built tooling so that we could exactly know which part of the system is slowing down and why is it slowing down. Is it because of the code or the data or some other physical infrastructure issues? And whenever we thought that we had enough instrumentation, something would happen, and we would have to go back and add more stuff. So this is something which I wish, again, I could say, I think we are done. But as we are scaling the system, we find that there is no such thing as enough monitoring. We want to keep adding more and more. Once we had this insight, we also wanted to make sure that we are able to recover gracefully and not require human intervention when something goes wrong. So we built inbuilt graceful degradation, where we built libraries where every publisher of a message was constantly looking at the queue length. As I mentioned, the queue length of pending messages in SQS is the best signal you get about something being wrong in the system. So we built sophisticated logic around making sure whenever you try to publish a message, you would look at the queue length and stop publishing when the backlog is high. This eases up the pressure on the system and allows it to recover. At the same time, we also had to make sure that we don't drop messages, because remember, these things are actually what people rely on to consume data at Dropbox. So we had a separate system which we built, which would keep picking up these messages and put them in the queue at a much, much slower pace, at the same time making sure the system is not falling over, but making sure that the end result of something happening to a system is that for some users, these updates become slower, but we don't forget about them. But the majority of our users are still able to get the experience they expect from us. So this entire system took us about 6 months to build, as I mentioned, with a team of 2 teams. And thanks to the work we did and a bunch of help we got from Amazon, we are able to run the system at an extremely high scale. To give you some numbers, at this point, we are running the system over almost 25,000 cores, spread across 5 different virtual clusters. We are running as many as 23 handlers. Each handler is essentially trying to take some kind of input and process it and output something. We, on a normal day, send about 20,000 QPS to SQS, but we easily burst up to as much as 300K. And this is where the power of SQS comes into the play, where they're able to scale themselves without us having to do anything. And at the current rate, we are processing almost 500,000 jobs per second. Some of these jobs are extremely time-consuming, like video transcode. Some of them take a few milliseconds. But the number of jobs we are doing with using this framework is almost 500,000. But we're not done yet. We're continuing to see extremely high growth, which means the systems have to scale. So scaling is obviously going to be a big challenge, and we are very happy to see that Amazon and SQS is going to be an extremely important partner, as well as someone who just almost makes us feel that they are infinite resources. We also want to build automatic regional failovers, where we want to be able to shift this traffic from one region to another region without any loss of experience for our users. We're considering adding support for more languages. Right now, these handlers have to be written in Python, but we are actively considering supporting languages like Go, as well as introducing containers to allow handlers to get better isolation from each other, both from a security perspective as well as making sure you're not impacting other handlers' performance. So what we talked about is a very specific system that we used to that we built to solve a problem which we had. But as I mentioned, one of the goals which I had for this talk was that hopefully you guys will also get some key takeaways from this talk. I believe event-driven computation, where the need to do some kind of processing where some file has, when some event has happened, maybe like a file upload or a file update, is an extremely common pattern. And hopefully a lot of you guys already have this thing running somewhere in your infrastructure where you need to solve this problem. In this case, we highly recommend SQS as an extremely powerful toolkit or a framework to solve this problem. It provides extremely high reliable messaging queue system, which, as you saw, we used to manage variable workloads. At the same time, leveraging Amazon and the elasticity which it provides to be able to handle variable workloads, where if you are in a situation where you cannot control or anticipate the workload you may have or you may see from your users, leveraging EC2 and auto-scaling is an extremely important thing to keep in mind. And the last but not the least, it is very, very important for systems which run massive workloads and have high requirements on latencies and throughput to build techniques and logic to detect and handle backlog. It will happen. In spite of all the scaling, all the work which anyone does, you will see issues which will result in a backlog. And while SQS and the building blocks which Amazon provides are very powerful, they themselves will not be able to prevent this from happening. So when you develop your applications on top of it, make sure that you actually take the time to understand where the issues can happen and how can we gracefully degrade, which is a more of an application-specific question. And this is pretty much what I had for this talk. Hopefully, you guys found it very useful. We also have a booth in the exhibition hall. If you have questions about Dropbox, the scale, or the problems we typically solve, please come and talk. If you have any questions, I'm very happy to answer them right now. How do you determine the visibility timeouts for different files, different sizes, and different handlers? Sorry, can you repeat that? How do you determine visibility timeouts in your SQS systems? Oh. So the question was, how did we determine the visibility timeouts for different files and different kind of handlers which we have? We used a very high visibility timeout. We tried not to be too clever about trying to say this. Some visibility could be lower, or we just have a very high timeout for all our messages. Yes? Yeah, so the question was, can I talk a little bit about error handling? So there are two kinds of error handling we see. Since we deal with user content, sometimes the data is corrupted. So the handler will not be able to just process or even generate a thumbnail because the photo was a corrupted photo. Those errors, actually, we have a retry mechanism where when the handler says something went wrong, we retry it a couple of times. But if it actually doesn't work, we then put it in what we call a purgatory. And we essentially say this is not going to get fixed by itself. And just we make sure that level of errors are very low because we don't expect too much of data being corrupt. There is other kind of errors which are more transient, which might happen because of the issues which we talked about. And there we are essentially hoping that retrying maybe 4 or 5 times, and the refresh, the recovery process I talked about, the automatic recovery, which is continuously running and picking up these messages which we failed to process, covers that. But we do see some errors which we can't fix because the data is just bad. Yeah, so we put in the out queue and then we mark them in the databases saying these things are, we are quote unquote giving up on these files because we can't do anything about them. Yeah. The question was any particular reason that we don't use auto-scaling? So the real honest answer is it hasn't come up in the list of priorities for us to do. So the way I think about auto-scaling is there are 2 benefits. One is it helps you save costs because then you can shrink your clusters if you don't need them. For us, that has not been a big concern. The other thing is it allows you to be able to handle spikes, which we don't anticipate. In our use case, what we find is spikes tend to be more where auto-scaling will have to grow very rapidly, and that doesn't work very well for us. So, but definitely something which the system allows, and we may get to it when one of these things become more important. Yeah.
Right, I have 2 questions. How do you prevent loops?
Sorry, can you?
How do you prevent loops?
Okay.
And the other question is, you mentioned that your producers stop publishing at some point in time. How do you prevent that creating an impact to your end users?
So there are 2 questions. One question was, how do we prevent loops? I'm presuming in the config file. So in the config file, when people are editing the file, we essentially do some very simplistic ways to detect loops. It's not very sophisticated, so technically you can create a very complicated graph. So while we have 23 handlers, the graph which we have is still manageable where people are not creating loops. So at some point that may become an issue, but right now we have not solved it. The second question was, if the publishers are stopping queue messages, how does it impact users and what do we do about it? So when the system does go into a backlog mode, we are absolutely impacting the users. And in the worst case, you can imagine what happens is we are dropping, say, majority of the messages coming in. And the automatic recovery process then kicks in and starts putting them back in the queue at a much slower rate. So in terms of degradation, it's much better than the system just kneeling over, because the automatic recovery is saying, I cannot handle, say, 450,000 jobs every second, but I can handle 100,000 jobs. So we are able to at least serve 25% of our users. And the system auto-corrects itself as things resolve. And we obviously get paged. So someone is actually using the monitoring we built to figure out the root cause and fix that issue so that the backlog clears up. Yeah.
Do you see a scenario where you might need your own
Do we see a scenario where we don't see? So I think that the answer to the question is there's a lot of legacy infrastructure things we have built over the last 7 years. So when Dropbox started, Amazon, I believe, just had EC2 and S3. So we have so much things we have built, which Amazon has now built to support other people that we already had to build internally, that is going to be a very hard migration. And it's not very obvious what it will buy us, because we're essentially going to be replacing something with parity. So it's more of a timing question. But do I see if there was a Dropbox today, then I think it probably will be on AWS completely. But we started 7 years back, so kind of timing issue. Yeah?
Scaling of the clusters that you mentioned, are you guys choosing reactive or do you use some kind of pre-warm strategy?
So, no, so we essentially, so when we use pre-warming in a sense that we just spin up a decent number of instances, and that should technically take care of what we think the load should be. We don't use auto-scaling, so it's not something where people can, the system will grow by itself. But if the backlog starts increasing, we essentially add enough machines to make sure that in steady state, the queues are near 0. Yeah, it's manual, right? Yeah?
SQS doesn't guarantee one-side delivery. How do you deal with that?
Sorry, can you?
SQS doesn't guarantee one-side delivery.
Yes, that's a good question. The question was that SQS doesn't guarantee once-only delivery. How do you manage that? So I kind of cheated a bit. So that particular thing is handled by the metadata. So remember that for every SQS, we are updating both the files and the metadata. So at the end, what handlers do is they make sure that when they're updating the metadata, so storing another copy of the file on S3, which is what the end result is not that is not an issue from a user's perspective, but it is actually very wrong if we start updating the metadata. So when we actually update the metadata, we have a kind of locking scheme which ensures that we're only processing a file once, not twice. But that's done in our data centers. On S3, we kind of just say it's OK for us to sometimes store 2 copies of a block, which kind of gets vacuumed asynchronously. Yeah?
Just curious if there was, you guys considered at any point as maybe a way to reduce costs, like having clients generate their own submails?
So the question was, have we considered, in terms of reducing the compute cost, having clients generate compute cost? I think in the world which everyone is moving towards, which is mobile and web-based, so web, there's no client. So people upload, and they actually use a website a lot. And on phones, it's obviously not going to, at least in the current, it's not feasible for asking phones to generate thumbnails. So we definitely don't think right now, but maybe if the advances happen very quickly, maybe. Just doing it for desktop PC doesn't seem valuable enough, given that a lot of our users are now mobile only. And photos typically also happen through phones. I mean, I'm sure all of us know that. So, yeah.
I have a mic, so I can be heard very well. Do you guys use the standard AWS management console, or do you have some internal solution or a way that you guys worked with Amazon to manage that better?
We have to use internal tooling. I do believe the console has improved a lot in the last year, but given the amount of instances, we're talking about like thousands and thousands of machines running, hundreds of, like the scale we have, console becomes extremely high. It doesn't allow us to do things in massive. So updating machines using the console doesn't work out very well. So we have our internal tooling, which is command-based. We don't have a GUI. Yeah. You can join Dropbox and you'll find out. No, it's a good question. As I said, join Dropbox and you will know. Oh, sorry. The question was, how much do we pay Amazon every month? It's more than $1. But we do believe we are one of the most important, and our relationship has been extremely good. So we have been working with Amazon for the last 7 years. So it's obviously, they have helped us scale a lot. Any questions? Yeah.
Coding
Yeah, so we don't use the transcoding service, which Amazon, I think, launched about 2 years, or maybe a year and a half back. And again, this goes back to what I was mentioning earlier. We built our own transcoding service about 2.5 years back. And so now we had it. And at some point, we may want to move, but it's like we have something that works. So, but yeah, so it's an in-house thing. Yeah.
I spotted what looked like Python class names in your YAML file. I was wondering what languages you use with SQS, and also whether you're open sourcing any of what you presented today.
So the language, the whole Livefill system right now is Python-based. So we're using Python for the entire infrastructure. In terms of open sourcing, we can definitely want to open source parts of it. Some of it becomes extremely specific to our use case. So we may have to like rethink about how to make it more generic and useful for the entire community. Like the handlers which we have are extremely specific to Dropbox use case. But the framework definitely can be separated out and open sourced, which we have to refactor code.
So Dropbox uses AWS for provide those all the service, and Box they build their own data center.
Yeah.
How do you compare the two different strategies?
So I think so. Our architecture is both. It's not as if we're just leveraging Amazon. Only Amazon. We have our own data centers as well. In terms of comparison, I think what our use case and our consumer base is much wider, much bigger, and the growth we are seeing is an order of magnitude different from what Box sees, both in terms of the data we have, as well as the number of quote-unquote petabytes we upload every day. So I think Amazon, in that sense, has been extremely valuable for us to be able to scale. For Box, I would imagine they decided that doing in-house makes more sense. I don't know what choices they had to do. But for me, I think it's a question of do you want to invest a lot in operational overhead or focus on building value on top of Amazon, which is what we would like to do. So we do have our own data centers, but we are very happy picking up things from Amazon if they're ready for us to use. Like SQS is a good example. We used SQS instead of using RabbitMQ or Redis, which also could have given us the same kind of functionality. All right. Thank you, guys. Hopefully you guys found the session very useful.